In today's class, we are going to look at noise. Now, what do we mean by noise? Normally, noise refers to any type of undesired signal, but there are several different types of undesired signals. So, we will take the example of a person talking. Let us say you have a person talking to somebody across the room. Right. So, you could have many different things. For example, you could actually have several people talking in the same room. Maybe people are talking across the room in this direction also, and somebody else is shouting, right, to a fourth person. So let us say person 1 is trying to talk to person 2 and person 3 is trying to talk to person 4, and let us say person 3 is shouting across the room to person 4. So that person 2 is not able to listen to person 1. So, this type of signal would normally not be called noise, but it would be called an interferer, because it is the source of the undesired signal, and the undesired signal has very specific properties. Maybe it is another person trying to communicate with somebody else. So, this would normally be called interference. But let us say just outside the room somebody starts using, let us say, a jackhammer or something like that to break some structure, right. So, outside this room somebody is trying to break, let us say breaking a wall, right. Somebody is actually breaking this wall with a continuous din, right. In that case there is no signal being communicated, right. This sound would be called noise, because this is not somebody trying to communicate with anybody else, it is an undesired effect of some other activity happening, right. So, for the purposes of this case, right, so we will point out that when we talk about noise, noise is physical or thermodynamic in origin, right. And what that means is, that means that noise is noise could be dependent on physical properties such as temperature, and we will see this in a few minutes, okay. But more importantly, noise is then statistical in nature, and therefore represented by a power spectral density let us call this some Sn of f. So, if I were to draw a power spectral density for noise, it may have some representation. I will show some behavior like this. Now, as it turns out, when we work with circuits, we normally look at the one sided representation in the frequency domain, and therefore, what we will do is we will take the signal content in the negative frequency and fold it over to positive frequencies, which means my noise will now get doubled, okay. So, this would be the single sided representation of the noise power spectral density. Now, in the case of circuits, when we say power, we normally represent it as voltage squared or current squared densities. Now let us start looking at taking some simple circuits, and we will start looking at the noise associated with those circuits. The simplest element that we will consider is a resistor. Let us say it has a value R. The noise associated with a resistor R can be represented in two ways. One is in terms of the voltage, the other is in terms of the current. If I represent it as voltage, let the two nodes be 1 and 2. I will represent it as a voltage in series with the resistance R, and I am going to call this En squared, which is the mean squared voltage in series with the resistance. And an equivalent representation is a current which is represented as a mean squared current In squared between the same two terminals 1 and 2. And because you are talking about mean squared, you can go between the Thevenin representation and the Norton representation. And in terms of Thevenin representation, you can say that the dependence between the Thevenin and the Norton equivalents is in the following way. En squared is R squared times In squared, or if you are talking about the mean squared, root mean squared RMS quantities, which I will represent as En and In respectively. This is the relationship between the two quantities. What about the value? Now the value of En and In are themselves physical in origin, and the expression is given in the following way. En squared, which is the mean squared voltage density, is 4 kTr, and therefore the mean squared current density is 4 kT by R. What does this look like in the frequency domain? If I were to plot these two quantities, let me plot En squared, and again I am going to, this is the one sided value. So, if I were to plot In squared as a function of frequency, clearly because it has a constant path spectral density, the value is 4 kT by R, and it does not change with frequency. Such a source of noise or such a type of noise is called white noise. White noise is a noise that has a constant path spectral density with respect to frequency. So, the second type of element that we will talk about are inductors and capacitors, and it turns out that inductors and capacitors do not produce noise, they do not have any noise associated with them, and that of course includes transformers also. I will represent that as M. So, inductors, capacitors, transformers do not have any noise associated with them. However, if you have non-ideal inductors, for example, if you represent the series resistance of the coil used to create the inductance by a resistance R, this will have thermal noise. This will have resistor thermal noise, but this inductance will have no noise. Next, we will look at a MOSFET. The MOSFET of course has 3 terminals, drain, gate and source. Since the gate current is 0, there is no noise associated with the gate current, but there is noise associated with the drain current. And I will represent that as ID subscript n the whole squared. Now, clearly the MOSFET has 3 regions of operation and the noise of the MOSFET is different in each region. When the MOSFET is off, for example, when the gate source voltage is smaller than the threshold voltage, the device will have no noise because it does not conduct. In the triode region, the device has a conductance GDS that is given by dou ID over dou VDS. So, GDS in the triode region is given by dou VDS of the current expression. The current expression is mu n C aux W over L into VGS minus VT times VDS minus VDS squared over 2. So, we have to take the first derivative with respect to the drain source voltage, and this GDS is given by mu n C aux W over L into VGS minus VT minus VDS in the triode region. And therefore, it turns out that the thermal noise associated with the device in the triode region is given by the squared current density is given by 4 kT times GDS. The third region of operation of the device is the saturation region. In this region, the device thermal noise happens to be dependent on the transconductance rather than GDS, and this is given by 4 kT times a factor 2/3 times GM, or 8 kT by 3 times GM. This is the thermal noise of the device in the saturation region. So far, we have been looking at the thermal noise of the MOSFET. It so happens that the MOSFET also has a different type of noise. So, please note that the thermal noise is flat in nature with respect to frequency. they all have constant power spectral densities and therefore they are white noise sources. The next type of MOSFET noise that we are going to look at is called flicker noise. So, when the MOSFET is in the saturation region, the MOSFET has one more source of noise and I am going to refer to that as ID 1 over f squared. This is also called 1 over f noise because the power spectral density is inversely related to frequency. In the saturation region, the device has a 1 over f noise that is related in the following way. The 1 over f noise current density is given by some constant k over W times L times Cox times Gm squared over f. So, there are several things to note for the flicker noise. So, number 1, flicker noise is colored noise, that is the noise spectral density, the current squared mean squared spectral density does vary with frequency. Number 2, flicker noise is normally present when the transistor has a bias current. In other words, in the saturation region. You do not expect to see flicker noise in the triode region where normally the transistor is used as a resistor. Number 3, because of 1 over f dependence, you expect flicker noise to be dominant at very low frequencies. We are in a minute we are going to draw the spectral content. Finally, this flicker noise or 1 over f noise has a process dependent parameter which is called k 1 over f. And therefore, different processes could have different amounts of flicker noise. Now, the reason this happens is because flicker noise is related to unwanted traps in the silicon to silicon dioxide boundary inside the MOSFET at the gate oxide to the channel interface. So, when you build the MOSFET, you may have unwanted traps in this region, in the interface between the substrate, the channel region and the oxide. and when you have them, you could have charge carriers periodically being trapped in a random manner and released in a random manner again, and that causes flicker noise. And therefore, if you are able to build a process which has lower density of traps, you might very well have lower flicker noise for that process. Having said this, let us now draw the noise of the MOSFET. Let us draw the total noise of the MOSFET. I will first show the flicker noise. Let us assume that this is the, I am going to plot the total with the individual contributions also shown. So, I will first show the flicker noise in blue, and I am going to show it in a log scale. In fact, even better is if I show it in a decibel scale. So, if I do this, 1 over f noise will have a pass spectral density which looks like this. Since I am drawing it in a decibel scale, I will see that the magnitude of this noise drops at a rate of minus 10 dB per decade change in frequency. The blue color shows the flicker noise. In red color, I am going to show thermal noise of the device. Note that thermal noise is white noise, and it has a flat pass spectral density, and therefore, if you look at the total noise at very low frequencies, the noise is dominated by the noise of from flicker noise, and at very high frequencies the noise is dominated by thermal noise. So, normally you would expect that flicker noise is dominant at very low frequencies and thermal noise is dominant at very high frequencies. Now, how do you decide at what frequency each one is dominant? That completely depends on the values of GM, that is the thermal noise level, and K and GM and WL Cox. So that you would have a resultant noise corner frequency which is called 1 over f corner frequency. This corner frequency is completely dependent on the values of GM, K, WL, Cox, etc. Finally, one last thing to note. You can reduce flicker noise by increasing the area of the gate. So, the gate area of the MOSFET is W times L, and if you increase that, the absolute value of flicker noise is reduced, because flicker noise squared noise density is inversely proportional to the WL Cox. In today's lecture, we will look at one final topic for just a couple of minutes. Let us say now that I have learnt about sources of noise, let us say I have some 2-port network that consists of RLC and MOSFETs. Clearly, this two-port network is going to generate noise. So, I will call it a noisy two-port. I want to find some way to represent the noise of this two-port. Now, clearly, I can do it in two ways. I can take all the noise sources, and if I want to represent it in a system manner, I need to represent it with respect to either the input port or the output port. Just like at a very high level, just as we would represent the system parameters by the Z, Y, G, H parameters, we can represent the noise, the total noise produced by the two port, either at the input or at the output. Now, if you represent it at the output, it turns out this is not a fair way of comparing different two ports. The reason we want to represent the noise at the input and the output is to compare two different networks and see if one is noisier than the other. For example, I have two amplifiers with gains A1 and A2. I want to find out in a particular application whether I should use A1 or A2 with respect to noise. I need to find some way to represent this. If A1 was much larger than A2, if I look simply at the output, it is very possible that VON squared is much larger than VON1 squared is much larger than VON2 squared. So, in other words, the output noise of A1 may look much larger than that of A2, because if I keep increasing the gain of the circuit, the noise levels will look larger and larger. The important thing to note is we are really interested in signal to noise ratio. If you increase the gain A1, the signal at the output of A1 is also larger. So, we want to find out a fair way of representing it, and the fair way of representing the noise of a two port is at the input. So, we convert it to a noiseless two port with a representation at the input and in general they are represented by two sources at the input, a voltage source in series with the input and a current source in shunt with the input. So, you need both En squared and In squared in general to represent two ports with all range of input resistances and all range of source resistances. So, in general, any two port will have a En squared, a voltage noise source in series with the input and a current noise source in shunt. In the next lecture, we will look at some example circuits, MOSFETs, resistors, where we will calculate the input referred noise, current and voltage sources.